Hi. Hi, Rachel. Can you hear me? Excellent. So let me just try the screen sharing, and if this will work, then we'll set up. Okay. Almost there. Okay, I see that I can see my slides, so then we are ready to start. So may I just ask you for one more check? I will try to speak without headphones, and then let me know if it's better or not, okay? So okay. Hi guys, it's 4 p.m. here, so I guess that we are almost ready to start. It might be that a few more people will join us, but yeah, it's recorded, so maybe let's start. My name is Fifa and I will give this tutorial in English. This tutorial is given in 5 different language versions. So if you are looking for another language version, let me know, and then you can change the tutorial. Okay, before we can start, there is one very important link that I guess that you should access right now. It's this one, tinyurl.com/useR2022. All materials, source codes, and everything that is needed for this tutorial is there. So to reproduce all examples that we are going to have, you can just follow this link, access this web page, and what you will find there is a GitHub repository. Now you can see this GitHub repository. So then you will have link to the repository, link to slides in HTML, and link to source codes. If you are going to execute our comments, it might be easier for you just to download the source code and use this link. Okay, then sometimes I see that some people unmute, so please excuse me, but I will mute you during the presentation. And then for questions, of course, you can unmute and ask questions. So I think that we are ready to start. I hope that you can hear me well and yes, you can see everything. Excellent, thank you very much. There is more than 100 people that sign for this tutorial. So it might be not that interactive, but I will do my best, and I hope that we will still have some interaction. But it might be less interactive tutorial than with smaller group. Okay, anyway, we'll do what we can. So again, I hope that you can access materials. If you have any questions, if you have a comment, please use chat. I don't know how many people. Okay, someone tell me that I am muted. Okay, all set. I guess that all set is the last message, so we are really ready to start. This workshop is divided into parts. It will be working with R code. Will be you will be doing some exercises in your R sessions, and also I will be presenting some theories, some examples in the HTML format. So during presentation, I will not see your comments. If there are some questions, and if you know how to answer questions of other participants, please help them, please answer them. If not, then during the, let's say, sync sessions, I will check if all questions are answered. If not, I will refer to them. I think that this will be the best option. There is a question, do you need to work with R? I will answer this question shortly. We have few short sessions in which you can do some hands-on exercises, but it's not obligatory. You can kind of have like 70%, 80% of the tutorial without touching R. However, of course, it's much easier and nicer to learn these new functions through experimentation. So, of course, it's best to use R, but you can just listen to the theory, and it should be also entertaining to some extent. Okay, so then let's maybe move forward. I hope that you have all accessed the link. If not, there is also some materials attached to this presentation, and in this material there is only one slide with the link to these materials, so it should be accessible even if somebody is late. As I said, this workshop is run in 5 language versions, of course, and it's actually a fruit of collaboration with people from different countries. So here I just highlight the team that developed the materials. I am a professor of machine learning, and I'm working in Warsaw at University of Warsaw and also Warsaw Institute of Technology. I teach students of data science and similar specializations. Also, we have a workshop given in Spanish by Juan Correra. There is a Polish version by Anna Kozak. There is a Vietnamese version by Letien, and there is a Turkish version by Mustafa Kavus. Of course, you can ask any question during the workshop, but if you would like to contact us after the workshop, feel free to use these links. They will move you to the LinkedIn pages, and then you can ask questions, connect to us and do other things that is currently important, like give us some feedback or share some ideas for maybe next materials. And here's a photo of the team that is giving workshop today. I am the one on the right, so maybe it's not the most important. What is really important is that we are from the MI Square group. If you'd like to learn more about the software that we are developing, methods that we are developing, you can just follow this link. This might be important because the software that we'll be presenting is software developed by our team. We'll also mention some other packages, but you can blame us if something is not working, or also you can share some ideas if something is working. So yeah, here you find more information about our team. And here is the agenda for today. There are 2 large sessions, and there is a break in between. So these sessions are divided into 3 smaller blocks. After each block, there will be some time to do some experiments with R. So there are these do-it-yourself sessions, in which I expect that you will kind of try your own some R comments on the data set that I will present, or on some new data set. Also, so these are these bolded do-it-yourself sessions. Also, these blocks are divided in a way that we'll start like the main idea for this workshop is explainability and how to create responsible models. So how to evaluate these models, how to check these models. But in order to learn some tools for this evaluation, we need to create some models. So the first 2 sessions are actually kind of very short, very basic introduction to data exploration. Then we do a very short, very basic introduction to modeling. We'll create 3 different models, and having these models, then we can talk about explainability, about validation of these models. So these are the 4 parts that are kind of the cornerstone of this presentation. But in order to explain anything, we need to first create some models. So the first steps will be about this. Again, I think that some of you might just read all materials and everything is clear. Then, if you prefer reading than listening, you can just disconnect. However, you can always stay with us and help others to dig deeper. Also, if this material is very easy, there are some exercises which are for different levels of experience. So even if you are some advanced R programmer, you can find some new challenges there, and maybe it will also be interesting experience for you. I will talk about this experience more after this first EDA session. Okay, so till now, is everything clear? Can you access the materials? Do you see the agenda? Do you agree with the agenda? The hours here, the time is according to Warsaw time zone. So I guess that is -7, I think, something like that. +7, it's +7. But except of this, everything else should be okay. Yeah, if you have any question, maybe first try chat. If you will not hear an answer, then you can unmute yourself, and then I will kind of access your recording. Kasia, if you can hear me, I think that the person who I'm listening to is you. So you can mute yourself, and then everything will work. Okay, so let's go further. How this workshop is organized. So again, the main goal is to share with you few tools that can be used for exploration of complex models. Because to create good models, we need to have tools that help us to explore these models, help us to understand what is working, what is not working, how models are behaving. They might be very complicated, they might be really black boxes, but still there are tools to explore what is happening there. So I will focus on these tools. Also, to do this, because we have only 3 hours, I have some assumptions. So one assumption, this is actually very important, is that you are at least somehow familiar with R and somehow familiar with predictive modeling. To the extent that seeing the R syntax, you know how to read the R syntax. This will be useful to understand what is happening. And also, I expect that you are kind of familiar with some predictive models, because I will be not focused on tuning these models, validating, or doing some tuning of data sets to train a model. I will be rather focused on the next step related to exploration of these models. So at least some basic knowledge related to modeling is needed. Of course, you can ask questions, but some of these questions might be very long in answer. So I will assume that all of you have some basic knowledge. And during the workshop, I will share with you some techniques that I am using in my daily practice to explore models. I'm working mostly with healthcare data, and I'm creating a lot of predictive models. And of course, if these models are could be applied in future, they need to be validated, they need to be tested. So I'm using these tools to better understand models that I'm creating. And I hope that this method will be useful for you as well. So the workshop is divided into parts, and it should be on average 1/3 of a theory, let's say, or some intuitions related to methods. Then there will be 1/3 related to R code. I will dig into some internals, how to understand what is actually in these objects that we will be creating, how actually these methods work. To some degree, it's important. Maybe not all details are important, but some information about the structure is important, because then if something is not working, you know how to fix things or how to debug things. So, and also a third of this will be related to exercises that you can do on your own. So I will show you the executed outputs from executed R comments, but you can in parallel do these exercises on your own and see if everything is working, tune some parameters, check some options, and then see how these functions are behaving. The group is large, so there might be some problems. If there are some problems, please let me know on chat. I will try to check this from time to time. Okay, and then because there is a lot of people, I expect that you are on very different levels. For some of you, these exercises might be very, very easy. For some of you, might be harder. So if it's easy for you, maybe please check chat, and if there are some questions that you can answer, this will be awesome if you can help. Okay, great. So about the materials, actually, the materials that I'm going to show you are prepared in a form of comic book, and this comic book is you can access them. It's online. You can freely access all these pages. You can also buy a printed version on platforms like Lulu or Amazon. here are links to all these language versions. If you think that it's a cool idea to have such short comic that is an introduction to responsive machine learning, and if you can translate the comic book to another language version, let me know. This would be super cool. I will be going through materials from the English version, so you can also read slides, comic strips here if you will find some time for this, or you can do this later. Also, during the workshop, I will mainly focus on intuition related to methods. So if you are really interested in details, I guess that these materials may bring you more additional information about the details. Okay, so let's start the modeling. There are a few packages that will be needed in this tutorial. Yep. There are a few packages that are needed in this tutorial. Here are these packages. So let me just quickly say what I am going to do with them. Table 1 will be a package that we will use for very simple EDA, exploratory data analysis. Then Direct will be a package that we'll use for model exploration, explanations, and model analysis. And then ggplot2, of course, is a package that we'll use for tuning graphics. All graphics that will be produced today are ggplot2 graphics. So to add some titles, I am using gg2 package. And then these three packages, I will talk about them in a second a bit more. But these three packages are for modeling. So here I'm going to share examples related to decision tree, simple decision tree, random forest model, and also logistic regression with splines. And these are three very interesting families of models, and it's very interesting to compare them. You might learn a lot from these different styles of modeling. So that is why I choose these packages. But all methods that are going to that will be presented today, all methods work with other models as well. So you can use any package in R for predictive modeling, and methods for exploration will be working with other packages as well. But I am going to use these three. So I hope that you have all of them installed. If not, just execute this command, and then they are small, so they should be installed quite quickly. Okay, again, methods for model exploration, visualization, and exploration. This field is commonly named XAI, Explainable Artificial Intelligence. There are many different names, but this is, I guess, that the most popular phrase. So today, during the workshop, I may refer to responsible machine learning, but also I may use other names of these methods, and one of them might be XAI. Instead of slides, I found that it would be much easier for you to actually have the text written, because if something, if we have some lag related to voice or anything, then you can just read these things. So this is why I'm just highlighting parts of the text, and I hope it will be easier for you to actually follow the text. Again, I assume that you have some basic understanding of modeling. If not, or if you think that we are talking about some behaviors that are not clear, I strongly recommend you this book, Introduction to Statistical Learning. It's very good introduction to machine learning. It's called Statistical Learning here, but actually a lot of important intuition and theory and examples are covered by this book. Also, the XAI examples, the model exploration, is based on the book Explanatory Model Analysis, but the book is open, it's free to access, but it has like 400. So I will just present the most important parts of the book here. But if you are interested in details, again, access this book. Here, of course, I will be focused on R tutorial, R part, but in the book you'll find Python examples as well. Okay, so why should you care about responsive machine learning? Sometimes people have 2 hours of presentation. Why it's important? So here I'm going to spend these 2 hours for presenting these methods. So just very briefly, predictive modeling is being used everywhere, literally everywhere. You can find predictive models in very different places, and the number of predictive models will increase probably with time. Some of these models are very simple, like logistic regression or decision tree. Some of them are more or less complex, like deep neural networks or I know random forests or things like that. The complexity of the model is not important here. It's like having a model. Sometimes we'd like to understand how the model is behaving. And not everything can be read from the structure of the model, especially for complex models. So such universal tools to understand model behavior are needed. And I am going to share with you a few tools that are helpful for this. The example that I'm going to use here is related to COVID data. It's because there are some very interesting relations in the COVID data, and I guess that if I'm using use cases related to bioinformatics or finance, these use cases are not that easy to follow for everybody. But with COVID, unfortunately, most of us have some intuition, have some understanding what are the key factors. So here we can kind of confront model behavior with our intuition. And this is also very important for predictive modeling, because with these black boxes, if you will have nothing to kind of validate against, then we need to believe in performance measures like AUC or other measures. If we have some knowledge about the domain in which we are working, then we can validate model behavior against our domain knowledge. And here, I do not assume that you have very detailed knowledge about the COVID disease, but I guess that we have all some understanding how factors like age might contribute to the risk of death, and so we can kind of compare our expectations against the data-driven approach. So this is why I'm using this use case. Okay, and about the models, so 3 packages will be used today. RMS is for logistic regression with splines. This is, let's say, a modeling which assumes a very deep knowledge about the domain, because if we are going to model nonlinear relations, or if we are going to model interactions, then this needs to be explicitly written in the model formula. So we'll use this model. PartyKit is a very nice package for nice visualization of decision trees, and Render, this is kind of great baseline with random forest models that can be created with just 1 line of code. So I will be using these models, but everything is working for other libraries, and it's being tested on other libraries. So if you are a heavy user of MLR, if you are a heavy user of tidy models or Caret, you can find detailed tutorials how to use all these explainers with models created with these other frameworks as well. But again, for the sake of simplicity, I'm not going to introduce this very fancy toolbox. I will be focused on the 3 packages for modeling. And also methods that I'm going to present, these methods are implemented in a few different packages. I am going to focus on Dalek because this is the package that I know the most, but also many of these methods are implemented in Flashlight, and especially if you are working a lot with weighted data, I think that Flashlight might be a nice package for you, because I think it nicely handles the weights for observations. And IML is another package, and if you are working a lot with interactions, there are some additional methods for digging for interactions in a model. So you can find these methods implemented also in other packages, but the intuition is the same. The style of working with models is the same. So I guess that you can choose any of these models to learn about Xi, about responsive machine learning, and you'll quickly adapt to other packages as well. Okay, so I told that we'll be working with the COVID data, but let me maybe clarify that we are going to use artificial data, but based on real data set collected in Poland, to create a model that will assess the risk of death. Again, I understand that for some of you, this might not be that nice topic to discuss. Like, there are different implications related to this disease that hit us very hard. But I think that from the scientific perspective, it's actually a very nice data set to study. So forgive me, it's not a good example, but it will be, I hope, very good for additional purposes. Okay, so let's start. Let's load packages, and again, the HTML page that is presented here is created automatically based on this RMD file. So I am not going to switch to R to execute all these comments because this will steal us some time. I will just show you comments and show you output from these comments, but you can just execute all these comments on your side. So we need to create first model. So let me maybe move. Here is the description how the data was created based on some real data set that we have collected in Poland. What is important for us is that actually we have two data sets. One is COVID spring and second is COVID summer. There are two data sets because in our journey, we'll use different data set for modeling and different data set for exploration of models. I will tell you later why it's important. Moreover, with this disease, we see data drift happening in real time, like every wave is different. So the spring wave was kind of different from the summer wave. And here we can evaluate the model behavior based on some unknown future data. And here the unknown future data is this COVID summer. So this is why I'm having these two data sets here. They are similar in structure. The only difference is that the summer data was collected during the summer, and the reality is that the mortality was higher in the summer for some reasons. Yeah, it's common that our models are great, but then in production with new data, it's not that great, and we need to validate the model on new data. So here we will use this additional data frame for model validation. Let us see how the data looks like. So again, to access the data, I need to load the DALEC library, and then I can use head function to see what is in the COVID spring dataset. You see lots of features here. The feature that will be the most interesting for us is the death. We will be predicting mortality, so we'll be predicting the probability of death. And then all other variables could be used as exploratory variables, like input variables. Gender, age, some diseases, different types of diseases can be used for data modeling. In this example, we should see that some of these variables are not known in advance. Hospitalization, fever, cough, or weakness, these are variables that we can check or learn after infection. So again, this data was created in kind of real settings. And again, part of modeling is to understand which variables could be used for predictive modeling and which should be used. So in our case, if we are going to predict mortality rate before infection, we should not use these variables. So in a second, I will remove these variables. But this is how the data looks after the package is loaded. So we have all these variables, and then in the COVID summer, so in the validation data, you have same variables, however, for slightly different set of individuals. Okay, having these data sets, we could and we should do EDA. Again, I am going to focus on model exploration. So this will be very short EDA. just to remember that is important phase. Yeah, I could not talk about responsive machine learning without saying anything about data exploration. So this is very, very short EDA. And actually, I am going to use the table one function to create something that is commonly called table one in medical journals. So it's a basic summary of data set. And it is a summary of data sets for each variable. You can see what is the average or what is the fraction of people that died or not according to any certification produced with these variables. So for gender, we see that there is some very small link, but with other variables like diabetes, we see that there is some very strong link. There is only 2% of deaths in the group without the disease, and 15% of deaths in group with the disease. So it's significant. So again, these are some things that usually are being done during the data exploration. And here, I will leave these results here to return to them after our models will be created, after some exploration of models will be performed. Just remember that we will have EDA here. Also, I need to visualize. I think that it's always good to prepare some plots to visualize data. So here I have distribution for age. You see that, of course, there is only a small fraction of patients, of people with age above 75, and a relatively small fraction of people, babies, kids, with age below 18. Majority of people are between 20 and let's say 70. So let's keep this in mind. Also, I have this distribution with colors that corresponds to the status whether someone died or not. So these are raw data. I will refer to this later, having some insights extracted from models. So this is for continuous data like age, and here is a mosaic plot for categorical data. So you can see if the fraction of people that died is equal or different in different levels of categorical data. So here I can plot diabetes against death. So of course, as expected, people with diabetes, their chances of death are higher than people without diabetes. Okay, so to start modeling, I should remove variables that are kind of, for some reason not needed. I removed the cough, hospitalization, fever variables, and leave this data set only with kind of valid variables like gender, age, and diseases. So I will start modeling with these two data sets. So let me know if everything is clear up to now. Is it too fast, too slow? How do you feel about this? I really hope that you can hear me. Okay. Great. So then I see that we can proceed with similar speed. So let's start with models. Here I have a short exercise for you, but this exercise will be more useful during the next do-it-yourself steps. So maybe I will not create space. I will not do this break for this exercise, and now I will just explain how to work with exercises. I see a question how death was measured. So actually, it's a very important question because everybody will die, but some of them will die sooner or later. So here, the definition was that death within 30 days. So with other problems or deaths that occur later, they were not calculated. Here is kind of, in the real data, there was a strict definition of days within 30 days after infection. Infection, of course, is also a problematic feature to measure, but more or less this was the idea to look for these, let's say, quick deaths. I will show you examples only for the COVID data. If we have time, I will maybe show you some examples for other data sets, but usually will not have that luxury. So most of these examples will be for COVID data. But exercises, you can choose your weapon. You can choose with what problem you'd like to fight. And actually, there are 4 problems. So you can recreate all of these results that I'm presenting with the COVID summer data set. This should be super easy, and this is recommended for beginners. It should be enough just to copy all instructions to our console. Everything will work as expected. So this is the easiest possible approach to exercises. If you feel maybe more advanced, or if you finish this quickly, you can do all these exercises for another data set, Titanic imputed. This data set is also in the Dalek library. What is interesting in this Titanic imputed data set, there is no missing values. So no problems with data preprocessing. You can use just this data frame for modeling. So it's very, very, very easy to use. Also, the Titanic is a nice problem because we have again some expectations who will survive, who will die. Yeah, all these stories related to gender, all these stories related with class, you will see confirmation of these expectations in models that you will create. So you can also use this data set from the Dalek library to recreate all these examples. And this will be, it should be relatively easy. There are 2 other use cases that you can try. They are slightly more advanced. One difference is that the regression tasks. So these 2 are for classification, and these 2 are for regression. Methods that I'm going to present you work for both, because from classification, we actually use scores, probabilities or scores rated to one of classes. So we treat these scores as continuous output. So in this term, you can do similar operations on scores and on predictions from regression models. But if you'd like to try these methods on regression data set, you can use happiness train data, which is also in the Dalek library. It's nice because there are just few variables. So it's very easy to track relations between these variables. And also, these are a data set about happiness in different countries. So you can, of course, refer to your country and see how your country behaves in when compared to others. And we'll be talking about local explanations. So this is a nice data set to study. And the FIFA data set is probably the most advanced. It's because of a number of variables. There is over 80 features there and over 5,000 observations. So some calculations might be time consuming. And some explorations, methods for exploration might be complex because you have like 80 variables. So again, if you are advanced user and if you already finish other tasks, you can fight with the FIFA data. Here, the goal is to predict the price of football players. So you can also choose your favorite football player to make this even more entertaining. So these exercises you can do with any of these data sets, and it should work for only of these data sets. And if you will find examples in the source code trivial, too easy, just try more complex data set, and then they will take probably more time, and you will learn some new relations. There will be some different plots to explore, to understand. Okay, so here are 3 points to explore this data set, but yeah, maybe let me go further because I see that we should start actually the next point. So let me go to the Hello Model section. Hello Model section, we'll create 3 models. It will be super quick, but just to learn models that we'll be dealing with later. So we'll start with the very, very basic model, tree-based model. We are going to use PartyKit library. If you'd like to learn more about this library, you can try this link. There is a very good literature. There are a few libraries in R to produce tree-based models. I like this one especially because it works nicely with different target variables. If the target variables is continuous, binary, multi-label, multivariable, survival, it's working for different output variables, and also plots are very readable. So yeah, I like these libraries, but you can also try also another libraries that you like or you have some experience with. Here, this will be very basic setting. I will just provide the formula, predict depth based on all other variables, and I am setting COVID spring data, training data. Here I have three plots with different depths, just to show you how to control depth of a tree. But it won't be that maybe relevant in our case. As expected, in this data set, age is the most important variable. So most stories that I will be sharing with you, I'll be talking with you, are actually related with the behavior of age or some other important variables in the model. Okay, I see a question related to Titanic. So the Titanic data can be masked with other packages, but Titanic imputed should not be masked. So you can use Titanic imputed and then you'll be fine. And then I see a question related to p-value. So in the function, you can define which test should be used. By default, for binary features, I think it's a Fisher exact test. And for continuous feature, it's probably Wilcoxon test, but it can be checked in documentation, because I think that this is very smart function. It checks assumptions, and based on the assumption, use either parametric or non-parametric test. But yeah, so it's really nice function to quickly summarize the data. Okay. Conditional tree, it's a tree function, first, second, third. For modeling, I will use this function, this model. So it's a model created with stop criteria. Let's split nodes as long as the p-value for differences between nodes is larger than 10,000. So we end up with such model. In such models, this model is small, so we can actually understand how model is behaving. But again, we are using this simple model to compare this with another models. So let me use this model. Then let's create another model. This one will be created with Ranger package. Again, there are many different ways in R how to create random forest models. First, you can use random forest library, because you can use Ranger library, you can use MLR, MLR3, tidy models, many different choices. I am using Ranger for speed. It's, in my experience, the fastest, but everything will work with other libraries as well. So here, what I need to do is to additionally set parameter probability equal to true, because by default, many of these models do not produce probabilities, but produce classes. And I will need scores, probabilities, to explore these models in a more smooth way. So I just added this parameter. Except for it, I have just data set, I have formula, so it's a very basic setting for the random model. All hyperparameters are a default one, and I have a forest model that I will be using later. Why a forest model? There is a reason, like with decision tree, it is being said that deep decision trees have very small bias, but may have huge variance. So Breiman use actually the bootstrap principle to reduce variance of models. And yeah, here I expect that these models might be better than a single tree because we average across many weak trees that are created in the Ranger in the Ranger package in this function. Yeah, so there is expectation that this model might be better, but I will check this expectation later based on the validation data. Again, one function to create some model. Of course, you can do some tuning of hyperparameters. It doesn't matter for next steps. So the first model that I'm going to compare is logistic regression with splines. And I needed this model in order to have different behavior on at end of range of age variable. Right now, it might be kind of fuzzy. What does it mean? It will be clear in two blocks when I will be talking about partial dependence profiles. But these three models, they should have very different behaviors. Like with forest, I expect that to keep variance low, there will be some reduction through averaging. So I will see, I expect some shrinking behavior of the model. For logistic regression, it's totally opposite. I will expect some approximation behavior at the different ends of the age variable. I will talk about this later, but here, for people that know more about logistic regression, a small comment, these three models should have very different behavior. And then, with the use of techniques like PDP, ceteris paribus, and others, we should actually see how different are these behaviors. Right now, we just have three models: forest, tree, LR, LMR, RCS. RCS because here are cubic splines, and I'm using spline for age in order to allow for not only linear relations, I am allowing for some spline transformation for age variable. Okay, three black boxes. If you know something about these models, it's great. From now, I will assume that there are three black boxes. Someone created these models and gave them to me to validate them. Yeah. There's a question in the Slack about the forest model. So again, this is important, and this will be covered in a few seconds in detail, but different functions in R for modeling produce models in very different structures. And some of these models have some already implemented plots. So for linear regression, you can just use plot function based on the linear model, and some diagnostic plots will be created. For decision tree model, you can use plot function, and the decision tree will be plotted. But it's not true for all models. And for random model, you cannot just use a plot function to have some plots. So here I just use a print function, and this output is given by the print function. It's not for all models the plot function is overloaded, we would say. So here simple to this point, different libraries give you different features, and forest ranger model does not implement the plot function for random forest. But it's not a problem. In a second, we'll deal with this problem in a more uniform way. Up to now, we have three very different models. There are three different black boxes. So this is a problem, really. We'll start with exploration of a single model, but the reality is that in many cases, we don't stick with one model only. We actually have a few different models. And what we need is to compare these models somehow. So to compare models, we need to have very uniform functions that will understand models of different structures. And to deal with this problem, different frameworks wrap models with these uniform structures. So if you are working with tidy models, they have their own way to pack all important information into uniform model representation. If you are working with MLR, they have their own way to encapsulate the model. And for our purpose, we have used a Dalek approach to encapsulate. It's really important because we will be comparing models, so we need to make these models more similar in terms of structure. To do this, we are going to use explain function in a Dalek package. There is detailed information about the function here, but let me just explain what is happening here. So imagine that you may have models created in different libraries, even sometimes in different languages. Here, it doesn't really matter in which language the model is created. And from the methodology standpoint, you can use same functions for all these models because we will not assume anything about internal structure of these models. So what we need is just a common interface to understand how to ask for predictions and how to do some operations like data permutation. So to create this uniform wrapper, we need to provide some additional information about the model. And here are these additional informations that will make all models uniform in terms of features that we can execute on these models. So the explain function takes as a first argument the model. It can be any object. It can be a function. It can be a model created in any different libraries. So here, this is a tree model. Here is a random forest model. Here is a logistic regression with sprite model. So the wrapper needs to know a model on which will be analyzed later. Then, in addition, we need to provide data that will be used for analysis. This is because most function, and we'll see some formulas in a second, most function calculate some expected values or look for some expected behaviors, averages on some distribution. So you should provide distribution on which these expectations should be calculated. And usually it should be validation data. If you don't have validation data, you can use training data as well, but here I'm going to use validation data. So you provide data on which the model should be validated. And now I'm going to show you few functions. Some of them need to know also need to know the true labels, not only the data, but need to know the true labels, whether someone died or not. So for some functions this is required, for not for all, for all, but I will provide this just to put as much information as possible in the model. So I am providing model, data set, true labels, and then there are 3 additional parameters which are not important here, but I put here to make it more explicit. These arguments are guessed based on the model, but to be more explicit, I just said that this is a classification model, and some functions will work differently for classification models and for regression models. So this is for classification. This is classification models. I can provide label. This is useful because later I will compare many models in a single plot. So I need to have some names for this model to recognize which is which. So I can provide any name for a model, and I'm using the label option for this. So tree model will be named tree, forest model will be named forest, and so on. And the last argument, verbose, this is to stop printing very verbose information about the explainer, because the explain function are checking a lot of things related to the model, and in the output you will see like dozen of lines with detailed check if everything is okay. So to not spoil this instruction, I just turn off the verbose part. It might be used for some debugging. So here is how to create an explainer, and this is basically a wrapper over the model. So instead of referring to model, models may have very different structures. Now I will be referring to these wrappers, and from the perspective of methods that we're going to use, all these wrappers provide uniform interface to the model. This is important in order to compare different models. Okay, now let me see questions. Yeah, I'm excluding the 8th column because This is actually the column with the target, and it's not needed here. It won't be an error, but there will be a warning that the target is already in the data. Later, you will see that this will make plots a bit more beautiful because actually explanations will be calculated for all variables in this dataset. So if you would like to have a larger number of variables, you can just add more variables than those used by the model, and they will also appear in plots. This will be visible in a second when we'll be exploring a tree model, because in tree model, in fact, not all variables are here. We see that, for example, diabetes is not here. Yeah, so the model is not using the diabetes variable. But again, it will be presented in explanations because it's in this data set. So here I can provide variables that should be used for model exploration. The explain function, it can work with survival models. It's a bit trickier because here I assume that the model output is one number. With survival models, it might be, median survival time. It might be probability that someone will survive over 6 months. So there are some, tricky questions that needs to be answered. So it is possible. It's not trivial. So, but great question, and I think that we have some tutorials how to do survival models with Dalek. Okay, so just let me maybe summarize that here I use this explain function to create 3 wrappers that will be used later, and these wrappers are called model tree, model forest, model LMR. You can use most of kind of classical functions on these wrappers like predict. So you can use predict function with these wrappers, provide a data, and then predictions for these models would be, printed. So usually you can work with these wrappers like with classical models, but additionally they have uniform interface, so you can use further functions with them. Okay, so let's do something with them. And first step will be to evaluate performance of these models. Again, there are a lot of packages that can be used for model evaluation performance. Here, I am using the package, the functions from the Dalek package to make you more familiar with the syntax. Because I guess that most of you know what to expect from the model performance evaluation. So just to make ourselves familiar with the syntax, we will do this short exercise, and then we'll do some more complex stuff. And of course, for models, there is a lot of different measures that can be calculated. Selection of the measure should be related with the problem that you are going to solve. In our use case, I am going to use AUC because this measure nicely summarizes ranking, and actually my model was used for some triage to do some assessment to which patients have higher or lower chances of survival. So the probabilities were not that important, the ranking was important. So to evaluate ranking, AUC is actually a good measure. But of course, there are many different measures. Because of the time, I will maybe not dig into details how these measures are calculated. You will find a lot of detailed information about the behavior of these measures in the materials that were attached later. So either the EMA book or the comic book. So just remember that you can use all classical measures. Also, you can use measures from other packages. So for example, if you are using Yardstick, with tidy models, you can use measures implemented with Yardstick. If you have some other packages, you can also make Dalek kind of consistent with other packages. But here I'm going to use the AOC. So all functions that we will be talking about have very similar structure. So maybe let me just introduce the structure. It will look like that. There will be like 3 steps. One step is to calculate selected explanation. And there are 6 functions that I'm going to present today. 4 of them will be maybe discussed more with higher detail, but these functions have 2 components. Names of these functions have 2 components: model and here performance. Meaning of this component is important, and I will in a second tell you exactly what to expect from these 2 components. So then there are functions that will be linked with different explanations. All these functions take wrappers as a first model. So here the model forest is a first argument, is a output from this explain function. These models have uniform interface. We can in a second switch to our console and see exactly what is inside. But what is important, they have unified structure. So these functions know how to work with these unified models. And then there are some other parameters, sometimes important, sometimes not important. Here, the cutoff is actually to calculate statistics like accuracy F1. These statistics required binary classes. Because my model returns continuous scores, I need to transform these scores to binary classes with some cutoff, so I can just provide a cutoff. But it's not that important. I will be focused on AUC, and for AUC, I don't need any cutoff. So all functions work in a way that I will have the function. The function has overloaded print generic function. So here, just by using name of this object, I have some short summary, what is calculated with the explanation. And then there is a plot function also implemented for this object. And I will later show you how to use the plot function. So you can do many things with results of these functions, but one of them is printing and plotting. All of them should work with print and plot function. Okay, so in the print function, what I can see is AUC. There are other statistics, maybe not that important for me. Also, this is a valid object in R, so I can extract this data in kind of automated way. But here there are just 3 models, so I can just read this data and remember these values. But if you have large number of models, you can have a loop or something to work with a collection of models in a very automated fashion. So these 3 models, maybe what is currently important, the forest model and the logistic regression models, their performance is very similar. The performance calculated on the validation data is very similar. It's 0,944, 0,941. There is some difference, but it's very, 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 very small. So these models are very similar from the perspective of performance. They will be very different from the perspective of behavior. And I will refer to this later. And also we have this tree-based model. It's not that good, but it's simple, so we'll use it as a baseline. The performance of a tree model is slightly worse. Okay, so I said that you can always print and you can always plot explanations. With plots, usually you can choose kind of plot that you would like to see with additional argument geom. So for performance, there are different types of plots that can be compared. For regression models, you can calculate residuals and compare residuals. For classification models, you can create plots like lift curve or different curves. So the geom helps you to select the proper way of plotting model performance. Here I'm going to use ROC curve. So you can just use plot function, this explanation created with the model performance. And yeah, as a result, you will get a ggplot2 object. Here it's ROC plot. Let me just tell you about a very nice feature which applied to all plot functions in the DALEC package. you can provide not only one model, but 2 or more models, and then all of them will be they'll be plotted in the same plot. They will be compared in with the same scales. And this is really a nice feature because sometimes if you are struggling which model to choose, we'd like to see a behavior of one model contrasted with behavior of another model. So in all plot functions, you can just list different explanations, separated with a comma. So here, all these models are being plotted with the plot function. And what we see, the blue and red line, these are for, legend is removed with this team. But if you execute this line without the team, there will be a legend. So the blue and red are for random forest and logistic regression splines. And the green one is for tree-based model. Oh, it's worse, as we saw in these numerical characteristics. Okay, so maybe this would be a good time for exercise, but unfortunately I see that we're slightly behind of a schedule. So I will ask you to do another module to talk about the pyramid for model exploration, and then we'll have time for all 3 exercises. So I hope this will be easier for you, and for sure it will be easier for me to meet with the agenda. So let me maybe move this do-it-yourself part for the break, and now I will talk more about the other approaches to explanations. It seems dev as third 10 column. Dev as 10. I don't understand. I am afraid that I don't understand the question.
Yeah, I'm wondering if there's a new version of the COVID summer data or something. If we do head COVID summer, should we be seeing just 8 columns or 10? I think I see 10.
Now I know where the problem might be. Let me just find this part here. Okay. So first, sorry for going through this tutorial with that speed, because I know that it might be easy to lose some lines. I think that the problem is related with these lines. So initially, the data set has like 13 columns or 12. And here, in these lines, I am removing these additional lines. And only 8 of them will be used later. And then if def is removed with this -8, then only the 7 will be presented in the plot. But if you use all data sets, then probably you will have slightly different results. And in your results, other variables might be important, like hospitalization and fever. I am not using these variables in the modeling because they are not known before infection. But I guess that the difference is from this line. So sorry for this confusion. Yeah, I hope that this is about this line. So yeah.
Okay, thanks. I missed that. Yeah.
Thank you. Okay, so again, let's do this do-it-yourself session during the break. And now let me maybe show you the bird's view on all explanations, because the names of these functions should be easy to remember if you just remember one pattern. So the pattern is that all these techniques are aligned in a structure ontology that shows different, let's say, phases of explanations. And there are 2 important directions in this ontology. One important direction is left-right, horizontal dimension, it's whatever we are going to talk about instance explanations or dataset explanations. It's really important because if you are with statistical background, usually when we think about model exploration, we are thinking about the general average behavior on some new dataset, on a new population. And this is called dataset level explanations or global level explanations because they are kind of, not specific to a single observation, they are specific to the whole data set of the whole population. But if you are coming from the, let's say, machine learning community, quite often expectations are different. Quite often you have single instance, single prediction, and you would like to understand the behavior of a model for this prediction. So this patient has a survival 0.3, and what does it mean? Why the model gives this survival for this patient? So today I'm going to show dataset level explanations and instance level explanations. So we'll touch both sides. In names, the difference is that the dataset level explanations, they have names that start with model, because they are model level. And for instance level, they have names start with predict, because they are kind of prediction level or instance level or local level explanations. There are different names because different communities like to name these methods differently. So sorry for this confusion. But in this package, just remember that if something starts with model, then this will be a general, average, dataset specific. If name of function starts with predict, then it will be tuned for a single observation. So the model performance was about the general model. This is why the name of the function starts with the model. Okay, second dimension is this vertical dimension. It's also important because in the vertical dimension, we have detail of information that is extracted from the model. And on top, you have the smallest possible amount of information, one number that summarizes the whole model. And level after level, you have more and more detailed information. So we just started with this first, let's say, level. Here, prediction for one observation will be one number. A model performance for one model will be one number, AUC for the model. And now I will be talking about techniques, how to decompose these numbers to attribute these values to specific variables. So in the second level, we'll learn how to attribute model performance or prediction to specific variables. And then we'll dig deeper, and then we'll go to the third floor, in which we'll not only see the attribution of a single variable, but we'll see the whole profile, how a single variable behaves, how the model behaves with different values of this variable. And then we can go even further and dig deeper and do some diagnostic of the model. I think that we'll have just a few minutes for the last level, but we should cover the first three levels with maybe level of details enough to use this in a normal life. So, before break, I'm going to discuss the model parts. After break, we'll discuss the predict parts. We'll discuss the model profile, and we'll discuss the project profile. So before break, we'll do these three parts, and after break, we'll do these three parts. So let's go to this model parts. Again, what is the goal? Goal is to say that not only this model is good, this model is bad, but to understand which variables are crucial for model performance, which actually influence the model performance. And for different models, many techniques were developed to understand variable importance. So for linear regression, you have all these ANOVA tests, p-values. For random forest model, you have this out of back validation. For tree-based models, you may have Gini measures, different techniques for different models. Here, I am going to use model agnostic measures because we would like to cross-compare results from different models. So there will be some techniques that can be applied to any model. Okay, so let's talk about these techniques. This is actually called variable permutation technique, and it is based on some likelihood function or scoring function that is compared between two settings. One setting evaluates the model on the validation data set. The second setting is evaluation of a model on a data with perturbed values in some variables. The idea is that if the variable is important, then after perturbation, the model behavior, model prediction should be should be worse. So if you have some statistic that summarize the quality of a model, it might be some loss function, maybe AUC, might be something else, then we can calculate the feature importance by subtracting or dividing. There is huge, large number of variants. These two characteristics, the performance on original validation dataset and performance on dataset after perturbation. Okay, maybe let's see this in practice, and then it will be much easier to talk about this. So again, first thing is that all functions have the same naming scheme. First part is model because it's general for the whole model behavior. It's related to whole model behavior, and then it's parts because this is the first floor. It is related to which parts of data set are important. The only argument here is the model, and the result is an object that have these statistics, important statistics for different variables. Maybe let's plot these statistics because then it will be easier to talk about values if they are plotted. So here, by default, because this is a classification model, so the loss function is 1 minus AOC. It's 1 minus because with the loss function, the lower the better. So we need to flip the AOC to have this behavior. And then what is presented here is the performance AOC, 1 minus AOC, calculated for the validation data. These are these dotted line, and the data with permutated values in one column. So these are these bars. The bar ends here. It means that if the data is permuted in this column, then the 1 minus IOC will be like 0.18. It will be much higher. So this is important variable because destroying the variable, permuting the variable, will remove a lot of important information about that is needed to do a good prediction. So here you see the performance of model for each variable, and the longer the bar, the more important the variable. You can have additional parameters in the plot function. Here, by default, in the plot, you have this loss function. This is the loss function training data, validation data, and this is the loss function for permutated data set. With the additional arguments, you can plot not the loss function, but the kind of baseline loss function. So loss function with subtracted baseline. So here all bars starts with 0. Sometimes it's important, so this is just option. This is an option that you can use. What is super interesting about this is that you can actually calculate explanations for all models. So you see here that I'm using the same function model parts for all 3 models, and then I can use that just one function, plot function, and putting all these models after commas to have a single plot that summarizes importance in all these models. And let me quickly discuss this result. The additional parameters are not that important. They just remove box plots because additionally there are some information about uncertainty, but we don't have time, unfortunately, to go into details. So I will just focus on this part. 3 models compared, 1 plot to summarize 3 models. What do you see here? First, you can see the performance of a model on validation data. So here you have this, the performance of models on validation data. Also, you see how the performance degrades if one column is perturbed. You may ask the question, why perturbing values in a column instead of removing a variable? There is also a technique like it is called loco, leave one covariate out. But removing a covariate means that you need to retrain the whole model on new data set without this variable, which is sometimes very time consuming. And there is lots of problems with this. So permutation has this advantage that you don't need to retrain a model. You just work with a model that was kind of delivered to you, and you can still evaluate the importance on a variable just by permutation of values in a selected column or group of columns. So what you can read here, for forest, clearly age is important. For logistic regression, also age is the most important. Others features are to some degree also important. We see that forest actually utilize all of them. With logistic regression, these neurological diseases have almost zero contribution. For tree-based models, only these three variables actually have some impact on model predictions. All other variables have clearly zero impact on model predictions. Here, the logistic regression model is not that stable. After these permutations, the performance degrades so much that it's worse than in all other models. So it might be also some interesting feature. But in most cases, from such plots, what you can learn is if all these models consume features in a similar way. So if the ranking of features is similar in different models. And here it is similar. So for all models, the most important feature is age. The second most important is cardiovascular diseases. So in later examples, we will focus on these two models, on these two features, on age and on cardiovascular diseases. Yeah, it might happen, of course, that some models we have different behavior. In this example, it looks like that. If we will have time, then you can do this exercise for Titanic data. It's nice because then the class and age are both important, and there is some interaction between these two things. So it's nice to see how different models utilize information about the interactions. Okay, I see some questions. Let me. There is a question about model performance. It's not working. Yeah. Okay, so it was related to the previous question. Okay, so I think this is answered. Oh yeah, right. Right. You can use different statistics for different models. Actually, I guess that this is related to a tree-based model. So no, it's about random forest, so Gini statistics. But again, for different models, you may use different variable importance functions. Here, we are focused on things that can be done uniformly for all models. So Gini statistics can be calculated by default for tree-based models. It won't be that easy to calculate this for neural network models. So that is why we are not using such statistics here, because in most cases, at least I believe in this, we often end up with few very similar models of these different structures. So it would be great to have some tools to compare these models. And then you are restricted to tools that work with models of different structures. So even if something can be calculated only for tree-based models or neural network models, then quite common, it can be applied to, it cannot be applied to all models at the same time. Okay, your turn. So now we have like 5 minutes before break, and we have like 3 exercises. Let me do this in a following way. First, after break, my colleague will join and give overview of the SHAP method, of the next method. This is because in parallel I have a defense of my thesis, so now I need to disconnect and go for my defense, and I will return here in 45 minutes. But after the break, my colleague will join you and describe the breakdown method, and then I will rejoin and describe other methods. In the meantime, during the break, please try to do exercises, and then I will leave some time at the end of the workshop, and any question you will have to these methods, we'll answer them at the end of the workshop or just after the break. Yeah, just play with these methods introduced up to now. Maybe try to understand what is inside the explainer. Try to understand what is what will happen if you will use different data set, not the trained data, but the validation data. And then you can also manipulate the label of models and see how this influences the plot behavior. So yeah, let's do this that way. And after the break, we can, my colleague Kasia will continue, and then I will join you after my defense and to talk about next methods. So up to now, I hope that it was easy to follow. Thank you. If you have any advice what we should focus on later, you can always write in the chat. Without any specific request, we'll just follow with the agenda here. So yeah. Let's have a break and let's see in 30 minutes.
Not hear anything.
Hello, everybody. Could you confirm that you can hear me? Okay, thank you. So 1 minute left. So okay, I think we can start after the break. I will replace Professor Biecek, Przemek, because he has his defense, but he will be back. So don't worry, he will finish this tutorial. But now I will explain and introduce different explainability methods like breakdown and shap. Before the break, you look at the variable importance, and this let me return to this schema. And during last section, you will focus on model parts, so on the variable importance, how every variable contributes to the average behavior of model. What is the impact of every feature on the predictions in the global sense. So now we would move to the left side and do it something similar, but not for the whole model, but rather to one specific case, one specific observation. And most of maybe somebody know the technique, which is called Shapley values. I think this is one of the most popular approach to explainability, and now we will focus on it and also on the breakdown approach, a bit different, simpler, and not so time-consuming. Okay, so start from the SHAP. In the SHAP, the key idea is to use the conditional expected values, and we would like to split prediction of the model and assign every feature the impact on this prediction. And for linear regression, it is very easy, because for every variable we have a coefficient, so we can only looking at this few numbers, coefficients, we can say if the feature has positive or negative impact on the prediction. When we are talking about more advanced methods, models like random forest, gradient boosting, or even with the spline regression with spline, this problem is much more complex, and the Shapley value can split the prediction into specific into additive form. So for every feature, we can assign the specific number, a Shapley value for this feature. And how this is computed? We use the conditional expected values. So this is the we assume that we have some feature fixed to specific numbers, and we average the model prediction for this in these circumstances. And looking at the Shapley values, we can follow how the average prediction moves to the prediction for this specific observation, doing this condition, looking at the condition expected values. And this is a bit complex, maybe a bit overwhelming. So let's skip to the example, and I think it will be much easier to understand. Okay, so let's start, and first we create a new observation. Let's call this observation Steve, and for Steve we would like to predict the risk of that. Our model is already trained, so we would like to use these models and look at the risk factor predicted by this model. To create this observation, we build a small data frame with only one row, and we need to specify the value of every feature. So Steve is a man, his age is 76, he has cardiovascular diseases, but no, he is not diabetes, and no neurological disease, and kidney disease, and no cancer. So Steve has some healthy issue, but this is not very serious. And according to our prediction, here we use our random forest model to assess Steve risk of death. This is not very high. This is only 32%. And here we can see how this data frame looks like. And for every value of this feature, for every characteristics of Steve, we would like to assess what is the impact of this prediction of 32% of death. So here we use the function predict parts. It is similar to model part, but the first verb is different, because predict means that we work on the instance level. When the function name starts with model, it means that we look at the whole model, whole data set. And here we have the second part, that is parse. So it means that we would like to split the prediction into additive form. So we use the predict parse function. The first object is the explainer, and then we pass the new observation Steve for which we would like to find this Shapley values. By default, predict parts return as breakdown profiles is a bit different than the SHAP, because we are looking not only all order of the adding new variables, but we look only at on one specific order. And I think this is a very good example to understand what is behind the SHAP, looking only on the breakdown profile, because breakdown is, let's say, one specific example, one specific cases in comparison to SHAP. So when we understand breakdown, I think it is easy to understand SHAP. Okay, so breakdown profiles may be constructed as follows. At the beginning, we are looking at the whole observation in our data set, and we look at the average prediction for this data set, and this average prediction is our intercept. And then we use the conditional expected values, because we would like to create this conditional. We assume that the variables are independent, and we can replace the specific feature with one particular values, as it is in explain observation. So our Steve has his age is 76. So every observation in data set is its age is replaced with these values, and then we look at the average prediction for this a bit change observation. And then looking at the we fixed age as 76, and then we are going to cardiovascular disease, and because Steve has this disease, we fix this for the rest of the observation, and then look at the average prediction. And this average prediction was about 0.5. And this is the key part of the breakdown profile, because we need to define the sequences of which we will condition the observation. And then in the every step, for this selected feature, we fixed this feature to the specific value and look at the average prediction for observation. And the change of the this average prediction between two levels, this is our breakdown values. Here, this is the output of breakdown of predict parts model function. But here we can also add some distributions, because we can look at the distributions of the prediction in every step, and but the red dots indicate the mean values, and this is the average prediction is what we call the breakdown values. The differences between these two levels. Okay, so this is a breakdown, and breakdown is for one specific order of conditioning the variables, and SHAP is SHAP tries to keep these assumptions and average, and SHAP would like to estimate the all orderings of the sequences. So we have to use many breakdowns to create the SHAP. So we can create breakdown for all permutation of features, and then average this, and this will be breakdown. Will be SHAP. Sorry. So we can change the predict parts argument and type, pass it as SHAP, and then we will observe the SHAP values. According to the SHAP, the most important variable is age, and then is cardiovascular disease, then is the gender. The impact of remaining feature diseases is not important. Here we can also observe that which feature has negative and positive value, because when it is positive, the contribution is greater than 0. When this is negative, the contribution is less than 0. And we can also create this kind of prediction for every model, because this is model agnostic, and we can compare them to each other, looking at these plots. Here we can check what is the Shapley value for decision tree model. And this is very similar, because also the age is very important, and cardiovascular disease, but impact of gender is not visible here, because the impact, the contribution of gender is equals to 0. Looking at the logistic regression with splines, we see that also the age and cardiovascular disease is important. Gender is also important, and all of them has positive values. So in terms of the risk, it means that the higher, the older you are, or if you have cardiovascular disease, the risk of death is bigger. So this is positive, but in sense of the model, not in sense of the interpretation. And cancer disease, kidney disease, they are not observed in STIF, so and their impact is negative. So if you don't have this this kind of disease, is you're not so risky to die. As before, it is very easy to also to compare this, because every predict parse object is a ggplot. So we can combine them using patchwork library and make and contrast this these two plots next to each other. Here we can compare the Shapley values and breakdown values for render, and we see that this is a bit different, because in breakdown the contribution of all feature sum up to the prediction of model. This is not we cannot observe this in the Shapley values. This is a bit different, but when we are looking at the order of the disease is very similar, because also the age and cardiovascular disease and gender are the most important, and the rest of features are not important. But the main difference between these two methods is that breakdown is for one specific ordering, and Shapley values takes into account many orderings, so it should be better estimation. And because we use this many permutation of order of features, we can assess the stability of Shapley values, because we have for every ordering we have different breakdown values, so we can assess how the stability, how stable is this Shapley value, and this is represented by the box plot at the end of the bar. So the width of this box plot is the meaning of the stability of this Shapley values. Shapley values has one of the main disadvantages is that it takes a lot of time to compute them, especially when we have a big data set with many features. And breakdown advantage is that it's much simpler to compute this, because we don't have to compute every ordering. But in some data set, it may be misleading, because breakdown values may be much different than the Shapley values. So it is it's nice to wonder how to order the breakdown values too. Next to the Shapley and breakdown values, we can use the different methods of predict parts. Some of them oscillation is related to the ceteris paribus profile, and we will talk about in next part. But the most important is that we should modify the type to change the kind of the method, which we would like to use to split the prediction into the contribution of every feature. Okay, so I think this is the most important part, and I think maybe it's a good time for you to train to check your models, which you train on your data on selected data, and create new observation. Maybe you can create new observation, but also you can use one observation from the data set. and try to repeat these steps. If you have any questions, feel free to ask. Type it on the chat. Okay, I think that there are. Okay, sorry, I couldn't. I didn't see that I should enlarge this. Okay, this is the error, I see. Can Shapley values be calculated for variables that are not categorical? Yes, the Shapley values are also calculated for the continuous variables. And the procedure is the same as in the case for discrete values. There is no problem. Because we only think we should do this is we need to replace the variables with the fixed values. Okay, I have information that Przemek is with us, so thank you for your attention. I will give him the stage.
I'm really glad that I could rejoin. I see that you have very interesting discussion about Shapley values. So I guess that now we can continue. And just if you have any unanswered questions related to Shapley values, please let me know. If not, I will go further. I really hope that you like this tool, because the Shapley values are right now like the most important, the most common way to explain models. Based on these individual instance level explanations, one can aggregate these explanations and create some global variable importance by summing up some number of explanations. But they are very important, but they are very common, but not the only one. So let me maybe go for other examples, and maybe I will go along the pyramid. And now let's talk about profiles. Once we will discuss profiles, we can return to general discussion about different explanations and how they can be combined. So the next level in the pyramid, let me go to the pyramid, is actually model profile. Again, the idea here is that in the first level, we have a single number, like AOC or prediction. In the next level, these numbers were attributed to variables. So each variable got some score that summarized importance of the variable, and then it can be done for the whole model. These were the feature importance, global feature importance, and this can be done on individual level. we talked about breakdown profiles and Shapley values. There are also some other methods, but Shapley values are the most popular. And now the question is what we can do with this one number, because it might happen that the age is super important, and we have this information that okay, it increases the prediction by 20%, but it's not the whole story. We can still ask more questions. Okay, so what exactly is the relation between the age and the model? So this question will be answered by the third level in this pyramid. So let's go to the description, and this time I will start with the individual explanations, and then I will go to the global explanations. This is because the global explanations are actually aggregated of individual explanations, so it's much easier to understand the global explanations through individual explanations. There are different names, as usual, for these explanations. The one that I will be using here are ceteris paribus profiles, because the ceteris paribus phrase in Latin means other things being equal, and this nicely summarizes how actually these explanations are being calculated. The idea here is that for single observation, so we are in the setting of explaining individual behavior of a model for a single observation. So for this observation, we'll see how the prediction is changing along some variable, like age, or some categorical variable. So also there are other names. Very common is individual conditional expectations, ICE. I think that they are heavily grounded, especially in regression models. So yeah, you can find this name as well. Usually these explanations are connected, attributed with so-called what-if questions, because all these explanations answer some questions, and for model parts and prediction parts, explanations, the question usually is which variable is the most important, or which variable is the second most important, or is this variable important at all? With profile-based explanations, usually the question is, what would happen if value of this variable is different? So these are kind of explanations related to what-if question. They can be calculated again with function that ends with profiles, and for individual explanations we'll have predict profiles, for global explanations we'll have model profiles. So we'll use this function, and here is an example. This is the whole documentation. Here's an example. As with breakdown, as with Shapley values, there are actually two required arguments. This is the model and observation loop, a set of observations for which explanations shall be calculated. For all rows in this data set, here is the one row. For all rows, explanations will be calculated. By default, explanations are being calculated for all variables. But if you have large number of variables, it's good to restrict the calculations only to those important ones. So here I'll be focused on single variable age. So I can calculate explanations with the predict profile. There is some overloaded print function, but it's not that interesting. The most interesting is actually plot function. So I can plot these explanations. And how to read this plot? So the dot, the blue dot here, corresponds to this observation Steve. Having more observations, the data set will have just more profiles. But now I have one observation, so I have one profile. So Steve, I think he's like 75 years old, and his prediction is above 0.3. So this prediction and the whole profile shows what would be his prediction if variable age is slightly higher or lower. So you see the whole kind of profile of response only by shifting this single variable. Yeah, by changing the age of Steve, we can see where the drop is the largest, if there are any steep areas in which there is no change in prediction. And this is happening right now here. So we see that there is a, okay, these are expressions for the random forest model. Random forest aggregates predictions for a large number of trees, and this is very flexible tool which can identify either very smooth relations, but also very sharp relations. So we'll see in a second how it looks in comparison to tree and logistic regression. But just focusing on this random forest, we see that this model identifies a steep decrease in chances of survival around age 60. And now here, this is a very, very flat profile below 50. Of course, in the domain knowledge, we know that there is some small increase for newborns, but this model has not identified these differences. So we see what is the behavior of the model around this observation if age variable is being changed. Okay, again, I think that we can gain more if we compare more models. This idea was actually described in the Breiman paper in 2001, this famous two cultures paper. Breiman used this Rashomon perspective approach, in which he argues that having more models, we can see some behavior from many perspectives. And it's like here, again, we have these three models, so we can see what is happening around Steve from perspective of three different models. So I'm using the predict profile function for all of these models. The rest is the same. I am using the observation Steve as an example. There is a new argument here, variable splits. It is important here because by default, the question is in which points this profile should be calculated. So for some models, it doesn't matter because these profiles are very smooth, but sometimes if you expect large, sharp drops, it's good to have a more dense grid. So the variable splits argument allows you to precisely say in which points the model should be evaluated, so you control density on the of the grid. So I need this to have sharper comparison of these models. But I am comparing the behavior of these three models based on 8 variables for Steve observation, and I can plot all three models in the same plot just by providing this additional argument in the plot function. So what is happening? And here is also the answer for a question why we have these three models. Because we expect a different behavior. Again, for a tree-based model, we expect these very sharp drops. Because in the tree, as you remember, you can just scroll up and see that this is kind of binary situation. If age is below or above some threshold, and then the prediction will drop or be increased. For random forest, this is a vote of 500 of trees. So it's not that sharp. The function is not. It might be more smooth. And for logistic regression, we see a very smooth profile because underneath we have logistic regression with spline transformation. So these are cubical splines, and they will be. We do not force them to be linear. The relation is not necessarily linear, but will be smooth. And as we see, there are big differences, even for these two models that have very similar performance. So the forest model and the logistic regression model, they have very similar performance, but the behavior is very different. Like the tree-based model learned that, there is an increase with age, but it's kind of, maybe more robust. And the prediction on the end of the range of this variable is smaller than the prediction by logistic regression. This is kind of now maybe comment for advanced users, but if you remember the histogram for the age distribution, you remember that there is only a small fraction of individuals with age above 80. And now we are talking about the really far right tail of the distribution. So there is only a small fraction of individuals there. From the perspective of our AUC, this fraction will not be visible because they do not contribute that much in the general overall performance. There are just few individuals. But if we are doing some very detailed examination, of course, it's very important to know what is happening on these regions. We are calling them out of distribution, because these are regions that are not visible in performance, but of course might be very important for individual patients. So here we see that see this difference. What we do with this knowledge is up to us. We can look for a third model that will average these two, or we can decide based on our domain knowledge that one of these models is better because it has better behavior in the kind of out of distribution regions. But what is important, we can see what is happening. So now seeing this, we can take more informed decisions. Okay, so these are individual profiles. Again, there are 3 dots because each model may have a different prediction. So we have 3 dots for 3 models, but here there are summaries for a same observation for Steve. And this is for one observation. So again, we have this kind of 2 perspectives. Perspective from single observation, which is sometimes important during the debugging phase, that I have observation with very wrong predictions, and I would like to understand what is happening for this particular wrongly classified observation. Or sometimes it's important during the deployment, because in the deployment, you can imagine that you have some patient, the patient will kind of challenge your prediction, and the question will be, okay, why? So now we can in detail see what is happening for this observation. But quite common, during the model training, we would like to understand the global behavior of the model, not only for this single observation, but globally for the whole model. So maybe let me, now I have this time for exercises, but before exercises, maybe let me tell you how to aggregate these profiles for more observations to have a global perspective of a model. And then seeing these 2 approaches, it will be easier to see strengths and weaknesses of both approaches. So yeah, this is for continuous variable. You can do exactly the same for categorical variable. Here is this cardiovascular diseases. The only difference is that instead of continuous scale, you have levels, but it's a small difference. You will see which levels are how they are different from each other. I recommend you especially the Titanic data, because then you have few classes, and in these classes it's very nice to see how different crew members differ in terms of survival. So this plot will work also for features with more levels. Yeah. But let's see how to aggregate these results. Aggregate results, so variable profile. Again, profiles, but for the whole data set, model level analysis. There is a story, you can read about the story in the comic book. There is a formula. I will be maybe focused more on the intuition. Intuition is very, very simple. And it's totally clearly described in a figure. I will use this figure to describe the intuition. You can simply imagine that you have profile for all individual observations, and here these gray lines, they are for individual observations, and then the only question is how to aggregate these profiles. And the most common approach is to just average across all profiles. You have like in the data set, you have 1,000 observations. So you can average across all of them for age equals 0, age equal 1, age equal 2, age equal 3, and so on. And the average is called partial dependence. Let me scroll higher. So this is partial dependence. So this is this average across all these profiles, individual profiles. The partial dependence profile was initially introduced by Friedman in his paper about gradient boosting, 2001. In the supplementary materials, there were mentioned these partial dependence profiles. Friedman were using these profiles because he was most interested in the method, like gradient boosting. But then the question was, of course, how we can understand what is happening in the collection of trees. So he showed these profiles. They were not popular for many years. They were again popular a few years ago with this boom of methods related to model explanations. I see a question. So yeah, Benedict, please let me know.
Yes, I do have a question. That's super interesting. I was wondering if in the partial dependence plots, there's also a possibility of visualizing uncertainty. And I was also wondering, I worked before with regression, I worked with effects plots. I don't know if, if this is widely known, I don't know. Could you maybe describe the difference between the partial dependence plots and the effects plots? Because I'm not...
Great question. For regression problems and for linear models, this is the same. This is exactly the same. The only difference here is that partial dependence profiles, you can calculate this for any model. And then you can compare these models in a same plot. So it was, of course, possible for effects plots to compare different linear models, but now you can compare linear model with tree-based models. But the interpretation is exactly the same for regression tasks, because then you can present expected prediction, or it's, in terms of linear regression, the noise cancel out. So it's actually the average prediction. So this is exactly the same. I was using FX plots in most cases to present interactions. So here, I guess the most common use case is that we do not assume anything about the relation between variables, and these very elastic models like gradient boosting or neural networks, they found some relation. So we might be even interested in the main effects. So this might be some difference, but again, from the technical perspective, the same. I guess that these profiles are used for all models which are not linear models. And many of these techniques, actually, they were invented by statisticians under different names years ago. And here, what we really discovered is that they can be used for other models. And using them on other models, we lose, of course, information about we are losing some information about the behavior of these statistics, because for linear models, we have the whole theory how to calculate confidence intervals for effects. Having assumptions about the noise, with random forests, we don't need these assumptions, so we need to use some other tricks to measure uncertainty. But I think that many of these techniques are kind of rediscovered. So debugging is, in many cases, same like diagnostic analysis for linear models. But now we can do this for different families of models. And we can compare these fancy neural networks with tree-based models, with linear models to learn how they behave. So maybe last comment related to this, maybe a bit off topic discourse, is that my preferred style of analysis is actually to use some of these very elastic models like gradient boosting or neural networks to see what is the link between particular variable and the outcome, and then knowing what I can expect, I can either manually or automatically derive a more linear model or something that is close to linear model with these transformations kind of encoded more or less manually. So here, seeing this transformation, one can say that it's clearly two linear regressions. Up to age 60, you have one relation. After age 60, you have second relation. We can model this with linear models with just this breakpoint analysis. But yeah, so this is the same. I mostly saw effects plots for interactions and partial dependence for main effects, but there is no difference from a technical perspective.
Thanks very much.
Thank you. Okay. I don't know Morris method. I don't know Morris method, but I often have questions how it's similar with sensitivity analysis. And for me, it's very common in science that we rediscover same things under different names. So it may happen that it is the same as Morris method, but I don't know Morris method, so I cannot comment on this. A comment related to this ceteris paribus. These profiles I sometimes use under the name sensitivity analysis, in which we are checking how sensitive is model with respect to changes in one variable. So again, the technique is the same. There might be a different use cases. So in sensitivity analysis, sometimes you are checking a short interval around a point to see how quickly we can see some change. In these profiles, we see the model behavior on the whole range of the variable. But again, this is a different use case. It's not a difference from a technical standpoint. So I can just agree that the whole machine learning committee and statistical learning committee sometimes are using different names for same concepts, like features and variables. Here I'm trying to be consistent. In the comic, you will find a short, let's say, dictionary how to translate some names to another, but I'm sure that there will be different names in subfields for same concepts. Here, I guess that the main advantage is actually that these concepts can be used in a model agnostic fashion. So even something was developed only for tree-based models, like this variable importance. Actually, this is concept described by Brayman in the paper about random forest. He said that we should shuffle this distribution to see on this how the performance of the model will change. Here, the only difference is that now we can do this for any model, and this might be useful. Okay, let's return to the partial dependence plot. So this is the average across all profiles. We can calculate this average with higher, let's say, resolution, because again, by default, these points are centiles. So there is a grid of 100 points, but based on the data distribution, so they are centiles. In some cases, it makes sense to have more detailed distribution. So you can specify the grid in which the given variable shall be evaluated with this variable splits argument. I am forcing to have a uniform grid from 0 to 100 just to see this bump. And again, in some models, you can force monotonicity. Like with gradient boosting, many of these models have additional parameter monotonicity constraint. So you can force to have only increasing, decreasing relation between variable and the target. But many models do not have any constraints like that. And sometimes it's like we expect some behavior from our domain knowledge or intuition. And this will be probably with age. Like we will not expect that there is some magic happening around age 80 to see this bump, but there were some artifacts in the data, and model learned this artifact. And here we see that this boost around this age. So in the original data, this data is kind of shifted. So we have similar relations, but this is not the true data. But in the original data, there was also this bump, and then bump was a reason that there were some house for elderly people, and all of them get infected in the same time, and they have more or less similar age. So there was this not really a statistical sample. It was not a simple sample with same chances that we have good representation of the whole population. But if we don't have that strict control over the training data, we can miss such artifacts. Sometimes they are visible in the relation learned by the model. So here, by having denser grid, I can see this strange behavior. And these artifacts are kind of visible in the data. We can do with them different things, like we can concatenate or we can maybe limit the age to the 80 and then just create a new category with people older than 80. So there are some different things that we can do. What is important here is that we can learn these artifacts from profiles. So here we see this profile learned by the forest variable. But again, what we can do as well, the aggregation may be done in many different subgroups. So maybe let me just show you some possible subgroups that can be used here and discuss how they can be useful. So one is that you can force to aggregate independently in different subgroups defined by another variable, diabetes. So here is a profile for diabetes, and here is a profile for people. Sorry, this is the green one is the profile for people with diabetes, and the blue one is the profile for people without diabetes. How this can be useful? Actually, in the COVID case, it turns out that there are two very important variables. So it turns out that the whole story about the link between the mortality and the variables can be described by this single plot with two profiles, calculated separately for these levels of variables. But such profiles can be also useful to learn about interactions. And if you have time, I will show you these profiles for Titanic dataset. They're actually in the book. So in the book, all examples are based on the Titanic dataset. And there is a relation between the age and class. And for class, you see that in the class 1, there is almost no relation with age. These people survived. But with class 3, the lower class, age was super important. Being below 18 increased, it was a crucial factor. So plotting these profiles for different variables, like in this case class, can help us to identify interactions. But again, this is kind of exploratory. So knowing these tools, it's up to your creativity how you will use them. What is important here is that you can calculate the average for all observations or observations in subgroups defined by some variables. You can also, so here is the segmentation for another variable, cardiovascular diseases. These profiles are slightly different. Again, we know that there are different chances of having cardiovascular disease given a certain age. So if for medical persons, this can be a nice plot for discussions. For us, it might be interesting to see that these curves are not parallel. Again, exploration. What you can also do is not only to segment these profiles for given some variable, but you can automatically use some clustering algorithm to identify some clusters of observations and then to calculate average behavior for these clusters. So this is exactly what happened here. This argument k equal to 3 means that we are doing k-means clustering, and for these individual profiles, for all observations, we are clustered them with some centering for 3 clusters, and then we are plotting these 3 clusters here. How this might be useful? Again, for additive model, we expect that these profiles will be parallel. If models are not additive, then some individual profiles will be different for some observations than another observations. So with the clustering, we can identify the different behaviors, and then we can dig deeper to see what is different between these clusters. But this is again kind of exploratory analysis. We can see if the linked with age is same for all observations, or maybe there are some sub populations that we need to identify. So you can calculate average for observations. You can calculate average for some variable, or do some segmentation. The advanced topic is that you can aggregate these profiles not in this kind of intuitive, naive approach to take the whole profiles and they average across them, but there are some more fancy approaches. I do not have time to go deep into them. They are described in the comic book, but just to tell you why the basic average might not be our best solution. This is because of a kind of representativeness of these profiles. So again, let's see this figure, and these gray lines, they represent individual profiles for some observations. So now assume that variables are correlated. So it might happen that I cannot change age, leaving all other variables unchanged. The core principle of the ceteris paribus profile is that I leave all other variables unchanged, I change only age. But if all these other variables describe features like, let's say, diabetes, cardiovascular diseases, cancer, of course, it's more likely that people with all these diseases are older people, because many of these diseases progress, develop with age. So now it might be unfair to take an observation that is like 80 years old, calculate the whole profile, then average the whole profile into the the model level summary. So the modifications that are called margin profile or accumulated local profiles, these modifications deal with the fact that if variables are correlated, one should accumulate only parts of these profiles to be inside the, let's say, the main fault created by the data. To avoid such situation that this observation, we now change variable to 0, but leave all other diseases common for this age group. So there are some other modifications. However, I need to share my experience with you that even if these other modifications are, let's say, more valid from statistical perspective, because they take into account all these factors related with the correlation between variables, it's sometimes hard to explain them for non-technical users. So if you work in, let's say, a credit scoring scenario, sometimes you need to explain your models to, let's say, business. And it's much easier to say that, okay, we have partial dependence profile, which are just average across all profiles. Then it's much harder to say that now we have this integral over some small changes which are derived based on some local similarity. So this is maybe a challenge for this field, that many of explanations are so complex that they are black boxes themselves. And if we need to communicate with stakeholders with non-technical knowledge, we also should use tools that will be easy to understand for them. Without this, they will be just scared and they will, lose contact with them. Okay, but this was off topic. That partial dependence profiles are just basic tool to summarize individual profiles. We have larger number of methods in this family, and you can learn them in the book. What is also maybe interesting, and I would like to focus on this, is model comparison. So previously I compared models for single observation. If you are a statistician, like me, you may think that models work more or less globally. So if some relation, this is at least my default approach. If some relation is true, more or less it will be true for all points. But it's for very complex models, of course, it might not be valid. So it may happen that individual profiles are very different from global profiles. So even if we solve the story for individual profiles, now let's see how it behaves, how it looks like for the whole population. So now, with the use of the model profile function, I calculated partial dependence profiles for all three models. And in this function, I have these global summaries of all three models. In the previous plot, I had local summaries. They were slightly different. Here, these summaries are average across all or at least many observations. If you are interested in technicalities, you will quickly see that in many cases, it makes no sense to average across million of points because the average will be very, very stable. So it's enough to sample 100 points and do the calculations much quicker. So there are some default settings in the like package that if the data set is large, there is some sampling used to deliver results quicker, to have some quick feedback loop with the person who is doing the modeling. Okay, so global behavior for all models. For the tree-based models, we see some steps that are consistent with the tree that was visualized in the part 1. For the logistic regression with splines, we have a beautiful, smooth curve. It is not linear because it's logistic regression, but also because there are some splines involved. Of course, one can say that we can extract these polynomials from the model, but with cubical splines, it's in many cases hard to guess how the function looks like. So here we can just plot the function and have some understanding what is the relation. And we see that, yep, the, let's say, extrapolation here, it's clearly typical for polynomials. Yeah, it's very different than the behavior for tree-based models and the random forest models, because in the random forest we have average across many trees, but if all trees have this flat behavior at the tail of the distribution, then the average from trees also will be relatively flat at the tail of the distribution. So we see that even if the AUC was very similar, there was this 0.944 or 941, the behavior of this model is very different. And it's different because the differences are in this out of data distributions. And of course, one can say that why it doesn't matter if it's out of distribution, so maybe it's not that important, but it may happen that the distribution shifts. And with new data, we'll have people older, so then the behavior for older populations will be really important. So here, I guess it might be really interesting to see differences in behavior for those models, and they are clearly different in age 16. They are very different in age 90. Okay, that's a summary for these, let's say, most common methods implemented in the pyramid. So we covered model performance, at least to some degree. We covered model parts, model profile, model predict profile, predict parts. Now, I would like to have three things. One is the do-it-yourself session to try the code, to discuss problems, to discuss about the methods. Second, I would like to also open a stage for other questions, maybe not related with the software, but maybe there are some other issues. But before this, let me show you one more example. This one more example is hidden in these extras. because up to now we were discussing explanation after explanation like separate tools. But in practice, usually we are combining these tools to understand model behavior from different perspectives. And this approach, having different perspectives, can be easily done with a package Model Studio. So just with single line Model Studio, you can automatically create an application that will show you lots of different explanations for given model for some observations. So I will now switch to the R console. We'll execute this example, and then we can switch back to questions. Yeah, the Model Studio is working for single model, but you can also use more complex tools like Arena, and they are working for many models, but they are more sophisticated. You will find examples for them in the materials. Here I will be just discussing the Model Studio. So let me now switch to the R, and then I can show you at least this one code. I was so optimistic that we can do all the theory, all the examples, and also exercises within 3 hours. Yeah, but at least let's do this one example. Let me move to the end of this file. You can access this file in a GitHub. So I just load the Model Studio. I will execute this Model Studio command. It should take around 10, maybe 15 seconds. So I hope the results will be quick. Here you can see that sequentially different explanations are being calculated. They are calculated in a way that the final outcome will be plain HTML file that is easy to share with others. I will show you this dashboard in a second. I can now just execute the MS command. There is a new screen. Let me just make sure that you see the screen. So there was a pop-up with this screen, okay? And this is a plain HTML file. What is important, because now we can share these explanations with people that are not using R, do not have R installed. You can just share with them explanations and discuss them. So okay, what you can do here in this dashboard, you can just select some different methods. So let me choose some of them, and then I will do maybe some discussion. Okay, so you can create this dashboard with different settings. You can of course manipulate margins. You can have more ties and so on. But what is important here, you can just explore the most common perspectives for this model around selected observations. So here I have explanations for Steve. I have Shapley values. I have breakdown explanations. I have statistical paribus explanations. I see the whole distribution for a given feature. So now I can see, okay, the Steve is relatively old, 76 years. So he's more or less in the right tail of the distribution. The age is very important. It contributes a lot to the final prediction. These two different methods have slightly different assessments, but not that different. As you remember, Shapley values can be understood as average across all breakdowns, all across different permutations. So here we see that the breakdown is relatively close to, here we have 19%, here we have 16%, but this is not a big difference. So these explanations are more or less consistent. And now we can kind of change, instead of ceteris paribus, let's see partial dependence. And here maybe instead of Shapley, let's see feature importance. And we can compare local explanations with global explanations with this iterative exploratory manner to better understand what is happening with the model. And of course, for us, it's good to learn line by line how to use all these methods with very high control, but for kind of quick evaluation, maybe what is needed is this one line that we will just create a model and then create explainer and have this first iteration for model exploration delivered with Model Studio. So this will be kind of, no efforts to have first understanding of model behavior. And then, like with any exploratory analysis, we may spend as much time as needed or as much time as we have to check many different perspectives for models that we have created. A single model or many models. Okay, we have 20 minutes, so let's maybe spend this time on questions and on exercises. So please check if these exercises are easy to do, and if you have any question, please ask them at the in the chat or vocally. Also, I hope that the Q&A session will be interesting, but if you are interested in only the core material, so there will be nothing else, so you can also switch to other tutorials if you want. Okay, so first question I see. The question is about variables, continuous variables. So you can replicate all these analysis if you are working with regression models and classification models. So the target variables can be continuous and categorical. Same with other explanations. And in many cases, it's much easier to work with continuous variables than with categorical variables, especially for these profiles, because these profiles makes a lot of sense if you have the whole range of the variable. And for me, it's common to work with variables like concentrations or some other variables that I do not expect linear relation. So continuous variables help me to see what is happening across the range of the variable. So you can work with continuous variables, and in my opinion, you can even extract more information. So even you have categorized variable and continuous variable, it's better to use continuous variable for the exploration, and maybe for modeling, it's good to do the categorization. But for exploration, I found continuous variables more useful. Also, if you have variables with many levels, then these plots like profiles, model profiles, you can of course calculate these model profiles. Let me just find an example. Sorry, this will be here. Sorry for this. This will be here. You can of course calculate such plots for levels, but with many levels, like 100 levels because you have school or hospital effect, then if the order makes no sense, these plots will not be that readable. So yeah, you can work with continuous variables, and actually I think that this is really the better way. Okay, next question. Dala explain, creates data training tests data set automatically. Here not. Actually, I'm working on package Forester. The package will support the modeling phase as well. So this package will do both modeling and the kind of data preparation. But here, user can specify any data for explanations. So it can be training, testing. The DALEC do not touch this part. Let me maybe have here a short discussion when the validation data will be better. So if you are using explanations that are based on model performance, like variable importance, that of course it's better to have a good estimate of model performance on new data set. So then if you're working with variable performance, it's good to have the validation data for explanations. But for other explanations, this split is not that important. You can calculate profiles even for training data, so you can still use the training data. And for statisticians like myself, actually I was trained to do a lot of model analysis based on the same data. So we were calculating this R-square coefficient based on the training data. Yeah, we are calculating p-values on training data. So yeah, it's up to you on which data set you are doing calculations. If you expect that the next data set will be different, what is also useful is to compare these explanations with same model and different data sets. Examples in this tutorial were related with 3 different models. It was random forest, logistic regression, and classification tree. But all these comments can be done with same model and different populations. So if you are working in a business in which you expect that there might be some turning point or change in model behavior, data, some change in I don't know, data structure, then it might be a good idea to have the out-of-time sample and compare the model behavior with the different time slots. Like here, I could compare the COVID summer, COVID spring, and because of the difference in mortality, we will see that actually there are some differences in the model behavior because these two populations are different. So you can compare, you can choose any data set, both training and testing, and sometimes it makes sense to compare same data set on different data sets. So same model on different data sets, if you expect data drift or some similar concept. No, I'm glad that you like this tutorial. So thank you for this nice words. Variable importance. In part 3. Okay, this is related with the variable importance. And I guess the question refers to this, this plot. Here, what is presented in these plots is not the difference in loss functions. Like I told you that in the formula, I am comparing the loss function for the original dataset and the permuted dataset. But actually, in some cases, you can learn a lot even when you compare the original loss functions. So here, these dotted lines, these are loss functions for models that we have created. So this actually, this one minus AUC. And you see that the tree-based model is worse. Actually, what is interesting, the tree-based model is worse even than logistic regression model after permutations in some variables. So you can use these models. You can specify totally random values for variables like cancer or gender, and still the model behavior will be better than the plain tree-based model. So here you have the original loss function. If you are going to have all these bars attached to a same point, like 0, then what you need to do is to use additional parameter type equal to difference in the model parts. And then all these bars will start with 0, as in this example. Without this, by default, the bars starts with the kind of baseline model behavior, baseline model performance. Yeah, I hope that this answers the question. There has been a lot of focus on ML algorithms replicating by society. Are there any tools or metrics that can help us? Okay, I guess this is related with fairness. This is a great question. I had a chapter related to fairness, but then I found that this is too much for this tutorial. But what you can do is to try fair models package, I will write name of this package in the chat, Fire models. This is also a package developed by our team, and it has syntax consistent with the dialect package. So once you have created explainers, you can use many different fairness statistics. And also there are some, let's say, procedures that can fix model in terms of fairness. So maybe small advertisement. The paper about fair models was accepted to the R journal, and it will be published in June, so hopefully in days. So the whole paper shows not only how to use, but also how to interpret the results. Because with fairness, it's really a tricky part, because some things can be done with tools, but some things related to fairness are really encoded in the data, and we cannot fix these problems without really understanding the pedigree of the data, how the data was created. So I think that we can have a separate 3 hours workshop related to the fairness. You can use fair models package to calculate all different fairness metrics, compares models with respect to these fairness metrics, but it's not only about metrics. It's also about the kind of, there are some very nice examples that problems related with fairness are really encoded with the future applications of the model. Like you can imagine a situation that you have two populations, let's say some minor class people from Mars, let's say, and we have the few people from Mars and some majority class, like people from Earth. And in the model, you can have a very good predictions for people from Earth, but bad predictions for people from Mars. Then you can easily fool some fairness statistics to have, fair metrics, but because of this unbalancing factor, there might be some problems in future use cases. So this is a story on its own. And there is an excellent book, Fair ML book, written by 3 experts in the field. Actually, these are guys from 3 large universities, I think Stanford, I forgot about the second, other 2. And they just give classes about fairness, and then they wrote this joint book. It's really awesome. FairML, I think .org or something like that. So yeah, I really recommend you reading this book. It touches the metrics part, but also it has a very good overview of the problems related with the data part and the problem related with future use cases. Because it might happen that for some use cases, model will be fair, but people will take this model and use the model in different settings, and the model for this new population will introduce some unexpected bias. Yeah, so great question. I don't have short answer, but definitely the FAIR models will be a nice package, and the FAIR ML is a great book to talk more about this. Okay, yeah, thank you. I guess that this is almost resources for rare diseases. So I do not have large experience with rare diseases. I have some experience with biological markers from SNP data, SNPs. So it was kind of genetic polymorphism. And then in that case, we are looking for rare diseases which are really linked with 1 or 2 genes. So in such settings, GWAS, so the genome-wise association studies, were delivering good results, much better than models that were using many variables. Because if you have really large disease, it's really hard. You need to have a lot of data to train a model that is using multiple variables. So from my experience, simple techniques were working best, just fitting individual univariate, bivariate models, controlling for some noise factor or something like that. But I do not have much experience with this. I will be looking under the GWAS collection of methods, because there is actually a large collection of methods, and many things depend on the details, like how many variables do you have, how many observations do you have. So yeah, I'll be looking under this GWAS, let's say, category, but no silver bullet, unfortunately. Yeah. So for this fairness, again, let me share maybe links to the package file models. So this package provides a model agnostic approach. And I know that if you are using MLR3 framework, MLR3 family has some new package related to fairness. I think it's called MLR3 fairness. Let me just confirm this. Yeah, MLR3 fairness. So if you are working with MLR3 package models, the second might be easier to use. And the fair models package is kind of model agnostic. You can use any model within this framework. And also, I noticed that some large companies provide separate platforms for fairness assessment. One of the oldest is IFE. It's delivered by IBM. So maybe let me just share this link with you as well. I find this okay. So right now, I guess that almost every company, large company, has their own tools for fairness assessment. So if you are working with H2O models, I guess that there will be something in their, let's say, zoo of packages. If you are working with scikit models, scikit learning models, there will be something there as well. The AIF is nice because they have really nice tutorials and materials, but you can find more for sure. And of course, if you'd like to talk about these things, we have like 3 minutes, but you can always connect with me on LinkedIn and ask question there. Or if it's more general question related to software, you can submit an issue at GitHub. And we are, of course, trying to do this in our free time. So maybe it will not be super fast, but there are a few people that are trying to read these issues and answer at least some of them. So this is also some approach to have contact with us and maybe have some deeper discussions about the model. Okay, this is all from my side. There is some question about the other examples. So in all of them, in most cases, you have the separate training and testing data. So for Titanic, for Titanic, you will find some examples, and then we are doing this manual separation for training and testing. For happiness, you have already these 2 data sets. Yeah, thank you for all these nice words, and yeah, let's have great conference, and hopefully someday we can meet on maybe another conference, because usually will be online, but there are some other conferences on site. So I hope that we can meet someday and have some discussion about explainability and fairness. So have a good day. Bye.